Alright guys, from your research, you should have found out that the kinetic energy is equal to 1/2 times the mass of an object times the velocity squared. You should have also found out that the gravitational potential energy can be calculated by multiplying the mass times the acceleration due to gravity times the height or the position in a gravitational field. And you could use these equations to find how much energy is in an object or in a system, or you can use it to predict quite a few things. You have a ball, there's a scenario for you, and you drop the ball and it hits the ground, and we'll say that here's the ball right before it hits the ground. The ground's at 0 meters and it falls from a height h. It falls from this height h. Now, we know that the potential energy up at the top is going to be mass times g times h. And we know that at the bottom, all of that energy, all of that gravitational potential energy gets transformed into kinetic energy. And it will all become kinetic energy if there is no outside forces acting on the system, or there's no loss of energy in any way, or it doesn't gain energy in any way. So we know that the gravitational potential energy before will equal the kinetic energy right before it hits the ground. And I'm going to put a little initial, a little final there. The gravitational potential energy before will equal the kinetic energy after. And the reason for this is the conservation of mechanical energy. The conservation of mechanical energy. Energy cannot be created or destroyed. It can only be transformed or transferred between objects. Okay. We can express this more specifically. Mass times g times h equals 1/2 times m times v squared. You see what I did? I just used these formulas and substituted them in. Question: does changing the mass affect the velocity? Does changing the mass affect the velocity? So say you do an experiment where you have a small mass and you measure the velocity, and then you do another experiment where you get a bigger mass and you measure the velocity. Well, you can see that changing the mass does not affect the velocity at all. In fact, the mass doesn't matter. They actually cancel out of this equation. They cancel out. The mass doesn't matter. And some of you guys were like, whoa, that is exactly what our data showed. Or maybe like, whoa, that's not what our data showed at all. When we changed the mass, the velocity changed. Well, the physics should be, if in a perfect world, changing the mass should not affect the velocity. Now, a few of you guys tried to figure out, how does the height affect the velocity? How does the height affect the velocity? So say we started out at height h, we drop it, and we get a final velocity that we recorded. Well, let's take out all these things that are constant in this equation here. So I'm going to not think about gravity. I'm not going to think about the acceleration due to gravity. I'm not going to think about this 1/2 thing here. And I'm going to develop this expression. Height is proportional to the square of the velocity. I have to use this little fish thing because they no longer equal each other because I got rid of these constants, but we're talking just about proportionality. The height, but we can use it almost just like an equal sign. The height is proportional to the square of the velocity. What does that mean? Well, let's first solve for velocity and just go, the square root of the height is proportional to the velocity. That's pretty much saying the same thing. How does the height that you drop an object affect the velocity at the bottom of the ramp or the bottom of the drop? Well, let's think about this for a second. What if you quadruple the height? What if you quadruple the height? 4 times the height. So our first velocity right here, our first velocity is proportional to the square root of the height. But if we quadruple it, and have that 4 in there. If we quadruple it, what happens to the velocity? If we quadruple the height, we get 2 times. I'm taking that 2 out of there because you can solve for the square root of 4. It's proportional to the velocity. So before, the velocity was the square root of h, but now the velocity is proportional to 2 times the square root of h. So what we found out was that quadrupling the height doubles the velocity. All right, so let that sink in. There's a couple things here that are pretty tricky. So write this down. Write down this problem here and see if we can make more meaning of it in class.